from Strathclyde, who's going to tell us about 3D printing microfactories.
Thank you, Chris. Hello, everyone. It's fantastic to speak this year again. I'm a researcher working as part of the CMAC Future Manufacturing Research Hub that's coming to an end at the end of the year. And I will be talking about a 3D printing microfactory. So just to give a bit of background about the Hub Microfactory research theme, the idea behind the Hub Microfactory is to use as little material as possible to design an end-to-end continuous product to process to deliver a product. We're aiming to do so by using a lot of predictive tools, digital predictive tools, building models, using these approaches to reduce the material that we're using to design this process, but also using screening tests on a small scale to make it more efficient, the process development. So the context of my work sits in the hot melt extrusion 3D printing space, and where we are looking to control the microstructure of these tablets that we're printing, and therefore then control the product performance. And the research areas that I've been working on is developing screening tests for these hot melt extrusion and 3D printing applications, also assessing the formulation performance in this area, and overcoming technological as well as material limitations in this space. So far, when linking hot melt extrusion with 3D printing, this occurred in a two-step manufacturing process where in the first manufacturing process, you are making a filament by the means of hot melt extrusion. And this filament is then used as a feedstock material to feed into a commercial melt extrusion printer to then create your 3D printed dose form. Now, this process is very dependent on the properties of the filament, of the material properties, of the formulation properties. There are certain failure modes associated with this, either to the material being very brittle and breaking in the drive gear, or to the other extreme end is the ductile failure of the material. So it's just too soft, it doesn't have enough structure to be fed by a drive gear, or it buckles in the hot end. So we have published some data relating to this two-step manufacturing process a wee while back in additive manufacturing, where we looked at a range of paracetamol drug loadings in an HPMC polymer, afinisol, and what we developed was a screening tool to relate the material properties to the printability of these filaments. And we found that a big range in the medium drug loadings, 25 to 40%, failed to print due to ductile failure. So it was just the ratio of API to polymer was plasticizing the system so much that this just wouldn't work. So in-house, we've developed a 3D printing microfactory where we linked a small-scale hot melt extruder, an 11 mil extruder, which is the big gray box on the left, and then at the end we've bolted on a dosing device that allows us to print directly from the melt state of the material onto a print bed. So this obviously opens up the pharmaceutical formulation space, because we were able to print all these formulations that we were previously not able to print because of the unfavorable properties. We've just recently, last month, published a paper in additive manufacturing that uses the 30% drug loading formulation and demonstrates that. So that's quite a milestone that we have eventually got that out in the literature. I've also got a poster that talks a bit more about this, so in case you're interested, please come and see me. This is a video of the printer in operation. On the schematic on the left, the arrow indicates the view of how the video was recorded. We've not only processed paracetamol and HPMC on this printer, we've also looked at other Hub Microfactory model compounds like mefenamic acid, and there will be a publication coming out, or will be submitted very soon, relating to that. In terms of the predictive approaches, or how can we design the process with less material, we have developed some rheology screening tools, or we use rheology screening tools to identify the initial process conditions. We require about 1 to 2 grams of formulation to do that. So depending on the drug loading, that's obviously less API that's required. And that not only gives us a good initial starting point, but it also allows us to identify where are the limits in terms of the process temperature, for example. This slide relates the microstructure of the tablet to the dissolution profile, the product performance of these tablets. Again, this is the example of the 30% paracetamol drug loading in HPMC. HPMC is a polymer that tends to swell quite a lot when it comes into contact with aqueous media. And what we can see here is that on the for you right-hand side, the low infill percentage tablets all showed a very similar release profile. That's here at the top. And once we get to 50% infill, which is the data points in yellow, we're actually noticing a decrease in the drug release, and this is because now the swelling of the polymer is actually closing up the pores or reducing the drug release from the porous structure of the tablets. And then if we're even increasing the infill percentage of these filled tablets, they behave like a solid block because of the swelling of the polymer. This is a very recent activity. For some of you that were at the last open day, I showed the graph on the right-hand side, which relates to the tablet weight changes that we observed over the course of a manufacture. So we saw an increase in weight, which then stabilized and remained quite stable there throughout the course of the manufacture. So we wanted to investigate this, and we set up the hot melt extruder with the SIFT MS system that we have on site, with the idea to monitor the volatile organic compounds that come off the vent port during the manufacturing process. So this was a very initial trial, and we then collected a mass scan. We performed some principal component analysis on the data, and what I'm showing here on the right-hand side are the PC scores, so the principal component scores versus the sampling intervals, and what we could observe was that we actually have a very similar trend in the data, similar to the weight change during manufacture. I've said this already, this is very initial trial, so there's a lot more work to be done to really get to improve the quality of data. But we're hopefully going to do a bit more of this. There's also the linking SIFT MS with hot melt extrusion is also a part of Aaron's project. Aaron Smith, he's over there. He's part of a PhD student of the DDMAT project. So he is linking the SIFT MS analysis with hot melt extrusion and looking at different process parameters and how that might impact the degradation, or potential degradation of the polymer as such. If you have signed up for the lab tour, the setup, the SIFT MS in conjunction with the hot melt extruder, you will be able to you will be able to see that. And we also have Colin Hasty from Element Material Technologies available if you have specific questions regarding the SIFT MS. And you can ask him on the lab tours, of course, as well. There's also been a bit of activity in developing additional screening tests. In this case, this is a screening test looking at the tenacity or the stickiness of formulations in the 3D printing space. Why is this important for 3D printing? Thank you. Why is this important? The stickiness of the formulation to the print bed, particularly the first layer that is deposited onto the print bed, is absolutely vital for the process to be successful. Oh, I can have a big drink.
Do you need any more?
No, thanks. I think I'll be fine. Thanks. So that's why it's important not to be thrown completely here. So this is why it's important. So what we're doing is we're performing a tack test. We've got a sample sequence where we're introducing a sample to a parallel plate geometry that's preheated. We're lowering the top plate. They're in good contact with each other. Then we're removing the upper plate and we're measuring the force that's required to do that, and we're plotting that, the force versus the displacement, and we then get this force displacement curve, and the shape and size of this curve then tells us something about whether the formulation is sticky, whether it shows good adhesion, but it also tells us about the cohesive properties of the material, and cohesive properties may affect the dosing of the material during a 3D printing process. So we're actually sticking with the example of the 5 to 50% drug loading of 50 in alphenisol that I showed earlier. When we were assessing the low drug loading formulations, they showed very pure adhesion and also underdosing. And this screening test then allows us to identify or adjust our process conditions accordingly to overcome this or prevent this, and obviously speeds up then the development process because we know more about the system before we start using it. So temperature is obviously important. Is one of the key aspects, process parameters in the 3D printing space. So we have we've looked at thermal imaging these 3D printing processes. So I've already mentioned that the stickiness is related to temperature, and also that the stickiness is important for the success of the 3D printing as such. But it's also important when you think about the layer-to-layer adhesion of a tablet that you're printing. So if you can design your process that you're either getting very good adhesion or you're getting not so good adhesion, this can affect your disintegration of your tablet, and therefore you could control your product performance in that way. So by thermal imaging, learning more about this can help us change that or modify these aspects, but it also, the thermal load of the material during the manufacturing process also affects what type of formulation you're producing. So you can either if it's a lower thermal load, you can retain your API in the crystalline form and create a crystalline solid dispersion. And if you have a higher thermal load, you can then change the solid state to an amorphous solid dispersion. And again, that can affect the product performance. I've got 1 minute. Does this include questions? No, so I can still, I've got a video, it's not just a picture. Okay, so on the left, you can see the printing interface, and I've taped this black tape around it. This just improves the quality of the thermal image because it reduces reflection. And then on the right-hand side, the arrow indicates where the nozzle is, and this is the material is being laid down. So you can see these little blue lines as the material is deposited. What you see in the front is just a reflection from what's above. So just focus on where the material is deposited, and as you can see, the initial layers that are being put down, they cool down very quickly, but as you are adding additional layers on top, these layers do not cool down quite as quickly because polymers are quite good insulators as well. So you could adjust your process conditions if you wanted to change that temperature profile. So you could introduce a lot of cooling, or you could heat your print bed if you wanted, a certain temperature exposure for your product. So this is a lot of work some of the work that we're doing at the moment, which can help us then design our processes in a better way. And the most important bit, acknowledgements. Thank you to CMAC and the National Facility that supports the fantastic infrastructure that we have here. It's wonderful, obviously also the funding bodies, EPSSC. Particular thanks to Gavin and John, who I believe both are not here today, and Ekaterina. They are fantastic to work with. I really enjoy working with them, really appreciate their input, whether scientific or not. Also thanks to Sieve Technologies, Vaughn, and Element Materials, Colin, who's provided a lot of the on-site training, and Mark for the advice with that technology. And if you have any questions, please come and see me or come to the poster later on. Thank you.
So we have some time for some questions. I don't think there are any on the app. Indeed.
Thanks, Elke. I'm interested to think about the differences in dissolution when you change your infilling. So you go for that sort of fairly regularish lattice shape, and you could see it being printed out. Have you thought about different printing geometries? So like, it looks like the top of an apple pie, a little bit. Have you thought about sort of different? Are there ways to do different printing geometries so you end up with the same infilling but a different shape? And would that change your dissolution, do you think? Because you increase the surface area.
So yes, absolutely. We have had limited time to explore that space. I believe that Patricia is working in this area as well, that looks at changing the shape of the tablet and how she can maybe comment on that a bit more in detail. So yes, absolutely. We have not really had the resources to look into that in more detail. So primarily, we've been focusing on getting the MicroFactory running, to produce tablets, to look at what material properties do we need to process the material in this space. So the product performance bit has been, I don't want to say neglected, but it's just certainly not been the priority.
Thank you.
Thanks.
Any other questions? Let me try one. Elke, right at the start, you said one of the intentions of the manufacturing hub was to do this with as little material as possible. How successful do you think you've been in achieving that goal?
I think in terms of, because we're looking at secondary processing, we're still having to use quite a lot of material to really develop the process to be robust, and obviously we have to do repeated runs, so that increases how much material you use. But I would certainly say that by using the screening test, the rheological screening test, for the initial start of the development, we have a pretty good idea what temperature setting, what screw speed setting we need for what formulation, because we can look at all of these properties beforehand. So I think there's a lot of saving there. Certainly, there is opportunity for saving more.
Great. Thank you very so much. Thank you, Elke, again.